Hi everyone. In the last lecture, we discussed about boundary linear transformation or boundary linear operator, and we also discussed about how to define the norm of an operator. In this lecture, we are going to see the equivalent conditions or the different ways of computing the norm of an operator. So let us start with a boundary linear transformation. Let T be a boundary linear operator from H1 into H2. So most of the time we will be calling boundary linear transformation or boundary linear operator or boundary linear map. All give the same meaning. So let T be a boundary linear transformation from H1 into H2. So T is bounded implies then there exists K bigger than 0 such that norm of Tx less than or equal to K times norm x for every x in H1, and from this you are able to define norm of T as supreme of norm Tx by norm x, where x is coming from H1 and x is non-zero. This quantity is finite and we call this as the norm of the operator. Or the operator norm of T. Okay, now we can ask the following question: how to compute the norm of an operator? So we will be describing different conditions which are equivalent, which are useful in computing the norm of the operator. So let us discuss that. Let T be a boundary linear transformation from H1 into H2. Then we have the following: norm of T is nothing but supremum of norm Tx by norm x, where x is coming from H1 and x non-zero. This is the definition of the norm. And we say this is also equal to the fact that supremum of norm Tx, x is in H1, norm x less than or equal to 1, and again this is equal to supreme of norm Tx, where x is coming from H1 and in this case norm x is 1, and again this is equivalent to, or this is equal to infimum of k bigger than 0 such that norm of Tx less than or equal to k times norm x for every x in H1. These conditions or these quantities are same, they give the norm of the operator. Let us try to look at the proof of this one. So let us take n1 as supreme of norm Tx by norm x, x is coming from H1, x non-zero. This is exactly the definition of norm, and let us take n2 as supreme of norm Tx, where x is coming from H1, norm x less than or equal to 1, and take n3 as supremum of norm Tx, where norm x equal to 1. So this is x is in H1 with norm x equal to 1. So, set of all x in H1 with norm x equal to 1 is called as the unit sphere of H1, and let us call the last quantity as infimum of k bigger than 0 norm T x less than or equal to k times norm x for every x in H1. So, let us call this quantity to be N4. So, when we start looking at the statement, we have to look at t to be non-zero, because when t is 0, we can easily show that norm t is automatically 0. So, that is very clear, and t not equal to 0. Okay. So, let us try to look at the proof of this one. Now, if you look at N2 and N3, so easily N3 is supreme over a smaller set, supreme over a unit sphere of image of supreme over the image of unit sphere under T, and N2 is supremum over image of the closed unit ball. So, the closed unit ball is bigger than the sphere, hence, so clearly we can see that N3 is less than or equal to N2. Now, if you look at elements of the form x by norm x when x non-zero, they are anyway elements of the closed unit ball. Hence, we can say that if you look at the definition of this kind of elements, to look at x by norm x, so that is an element of the unit sphere. In fact, that is subset of closed unit ball. Hence, we can say that N2, so the supreme N1 is supreme over all the elements of x by norm x form, T of elements of that form. So, that is anyway less than or equal to N1. So, N2 we can say that N1 less than or equal to N1 less than or equal to N2. Okay. Now, let us look at we want to prove that N2 less than or equal to N1. So, let us take x is in H1 with norm of x1 less than or equal to 1. Then we have look at norm Tx. So, that is less than or equal to norm Tx by norm x, because norm x1 norm x less than or equal to 1. So, 1 by of that will be bigger than or equal to 1. So, hence we can conclude that norm of Tx less than or equal to norm Tx by norm x, but anyway this is less than or equal to supreme over all such quantities, supreme over all these norm Tx by norm x, where x is in H1, x non-zero. So, we can say that this is less than or equal to norm 1. Now, right hand side is a fixed quantity, whereas left hand side depends on element x. So, we can conclude that. So, hence we can say that by taking supremum on the left hand side, we will get N2 is less than or equal to N1. So, we have shown that N3 less than N2, and N2 is nothing but N1. Now, we want to show that all these quantities are equal. So, we also look at N4 and other quantities. So, first we claim that N4 is non-zero. N4 is if N4 is 0, so then there exists a sequence Kn with Kn is bigger than 0 for every n in n. such that Kn converges to N4 as n going to infinity. Now, what is the property of Kn? This is second property is norm of Tx. Okay, so let me norm of Tx less than or equal to Kn norm x for every n, and we can conclude that Kn converges to N4. Okay, if now because of this condition, these two conditions, we can say that if N4 is 0, norm Tx is less than or equal to 0 for every x in H1. Just look at this one, this statement. When once Kn goes to 0, N4, if N4 is 0, norm Tx less than or equal to 0, but norm Tx anyway bigger than or equal to 0. From that we can conclude that T equal to 0, which is a contradiction. Hence, N4 cannot be 0. Okay, so we have shown that N4 is non-zero. Now let us, so clearly let us take x is in H1, x is non-zero. Then let us look at y as x by norm x. Okay, so let us take y is this one. Then look at the definition of N3. N3 says that supremum over norm Tx, x less than or equal to norm x equal to 1. So now if you apply by definition of N3, norm Ty less than or equal to N3. So clearly by definition norm Ty is less than or equal to N3. This implies norm Tx, so here it is 2. See, N4 is the least number which is strictly positive, satisfying norm Tx is less than or equal to N4 into norm x. N3 also satisfies the same condition from this relation. So we can conclude that so by definition of N4 we can conclude that N4 less than or equal to N3. So far we have concluded N3 less than, so we have shown that N3 less than N2, that equal to N1, and we also have shown that N4 is less than N3. So we have shown that N4 less than N3, N3 less than N2, that equal to N1, and if we are able to show that N1 less than or equal to N4, then we are done. We want to show that okay. Now N4 is non-zero. So by definition of N4, norm Tx is less than or equal to N4 into norm x for every x in H1. So here this is 1. This implies norm. So in particular, when x is non-zero, also this is true. So norm Tx by norm x less than or equal to N4 for every x in H1, x non-zero. Hence, by definition of, so left hand side is depending on x and right hand side is fixed quantity. So this is true even if you take the supremum on the left hand side. So this says that n1 is less than or equal to n4. So what we have shown is this quantity is less than or equal to n4. So hence all these quantities are same. So we have shown that all these quantities also gives every quantity that we have defined earlier gives the norm of the operator. Okay. In fact, they also suggest how to compute the norm. For example, if you look at N4 definition, that is in form of k bigger than 0, norm Tx less than or equal to k times norm x for every x in H1. It has a geometrical meaning. Let us look at that part. So this says that N4 is nothing but in form of k bigger than 0 such that norm Tx less than or equal to k times norm x. So first of all, we should find out a positive quantity k such that norm Tx less than or equal to k times norm x. So it is simple observation. If there exists k bigger than 0 such that norm Tx is less than k times norm x for every x in H1. Now if you take any number bigger than k, that also satisfies this condition. This implies norm Tx is less than or equal to L times norm x for every x in H1 whenever k is less than or equal to L. Any number bigger than k also satisfies the same condition, but the fourth condition, whatever we have defined N4, that says that you have to choose the smallest number satisfying this condition, norm Tx less than or equal to k times norm x. Now let us recall that whenever T is bounded, it sends bounded sets of H1 into bounded sets of H2. Let us write this as a remark. And given any bounded set, we can actually scale it to a closed unit ball. We can write any bounded set. If B is bounded, it can be put in a ball centered at 0 with radius m in the closed ball. Now we can scale it so that instead of looking at any bounded set, we can look at the closed unit ball. So we can easily show that T is bounded. We can show that T is bounded if and only if T of B01, the open ball centered at 0 with radius 1, and take the closure of that. This is bounded. Instead of looking at arbitrary bounded set, we can always look at the closed unit ball, and if we are able to show that that is bounded under the image of T, then we can conclude that T is bounded, because any arbitrary set we can scale. If we have a arbitrary set B, we can scale the closed unit ball in such a way that that bounded set is inside the closed unit ball. Now with this, actually we can get a geometric interpretation for the norm of an operator. We can actually look at this in R2. Now look at the closed unit ball here. Look at closed unit ball. Now under this, under the map T, it is sent to a bounded set in R2. So, let us take the bounded set is of this kind. So, this is T of B01 closure, because T is bounded, this set is also bounded. So, here it is bounded. Now, the definition of N4 suggests that look at the smallest ball containing this T of B01 closure and take the radius of that, that is exactly norm. So, since this is bounded, we can actually look at a ball centered at 0, radius like this. This is ball centered at 0 with radius r. Now, what exactly we are going to do is, instead of looking at this, look at a smallest ball. So, here the radius is this one. So, if you get a ball like this, so this contains the image of the closed unit ball under this map. Now, this one actually give the norm of the operator. Okay. So, norm of the operator is nothing but look at the closed unit ball in the domain and take its image. Since T is bounded, the T of the closed unit ball is bounded. Now, look at the smallest closed unit disk containing this bounded set, and the radius of that closed unit disk is nothing but the norm of the operator. Okay. So, this is a geometric interpretation for the norm of an operator. Now, let us try to look at a few examples of operators where actually we can find out the norm. Let us start with simple examples. The first one, let us fix a complex number, define T from a Hilbert space H into itself by Tx is lambda x for every x in H. This is nothing but scalar times identity operator. So, depending on lambda, you will get an operator. For example, when lambda equal to 0, you will get 0 operator. When lambda equal to 1, you will get the identity operator. So, lambda equal to 1, lambda equal to 0 will give T 0, lambda equal to 1, this will give T equal to identity, the identity operator. Now, here it is easy to find the norm of the operator, because if you look at the closed unit ball in the Hilbert space, now T of B is nothing but lambda times the closed unit ball. So, since norm T is positive, we can conclude here that norm T is nothing but mod lambda. So, easily by definition we can easily check that norm of T is exactly modulus of lambda. Okay. Let us look at one more simple example. Let us take lambda 1, lambda 2 to be complex numbers. Define T from C2 into C2 by T of Z1 Z2 as lambda 1 Z1 comma lambda 2 Z2. Z1 Z2 are coming from C. Now, with respect to with respect to standard orthogonal basis of C2, we can write T is nothing but T is equivalent to the diagonal matrix lambda 1 0 0 lambda 2. On C2, we can define the Euclidean norm, which comes from the inner product. Let us try to look at norm of this operator. So, here the trick is that we have to find out a k such that norm Tx less than or equal to k times norm x, and try to minimize that k. So then we can conclude that norm t less than or equal to k. Then we have to find out unit vector where the norm is attained, norm t is attained at that unit vector. That is the idea of finding the operator norm. Now look, so consider norm of t z1 z2. So this is L2 norm. We can say that this is let us take square here. Now what we can do is this is norm of, let us say this is z, norm t z. We want to say that it is less than or equal to k times norm z. Here norm z is nothing but square root of mod z1 square plus mod z2 square. But if you simplify, this is mod lambda 1 square mod z1 square plus mod lambda 2 square mod z2 square. Now look at if you take a number which is maximum of mod lambda 1 and mod lambda 2, we can say that this is less than or equal to m square into mod z1 square plus mod z2 square, where we can say that m is nothing but maximum of these two numbers mod lambda 1 mod lambda 2. So this is nothing but m square into norm z square, where z is z1 z2. So from this we can conclude that norm of tz square, norm of tz is then equal to m times norm z. So here also Euclidean norm of z. So we can say that from this norm of t is less than or equal to m, where m is nothing but maximum of mod lambda 1 mod lambda 2. If lambda 1 and lambda 2 are 0, then this is a 0 operator. So we are not interested in that. So since we are interested in non-zero operators, at least one of these complex numbers lambda 1 lambda 2 is non-zero, and when you take the maximum, anyway that you will get non-zero number. Now the question is the following: can we get equality? That means, can you get a unit vector where norm of that unit vector is exactly norm of the operator? So we are expecting that norm of the operator is equal to m. So can we say that there exists a unit vector where this m is attained? Okay, so suppose m is mod lambda 1 without loss of generality, assume that. So then look at t of 1 comma 0, that is nothing but lambda 1 comma 0. So this implies norm of t 1 comma 0 mod lambda 1, this is nothing but m. So this vector, let us say z, so norm of z is 1. We got a unit vector on which the norm is attained. I mean, we were estimating that we are expecting that norm of t less than or equal to m, but we got that at some point at some unit vector this m is attained. So we can conclude that. So from this we can conclude that norm of t is m. Okay. Now we can actually generalize this result slightly to a general setting. Let us define t from Cn to Cn by t of z1 z2 so on zn is lambda 1 z1 lambda 2 z2 so on lambda n zn, where this z1 where lambda 1 lambda 2 so on this lambda n are fixed quantities. we can actually check that in this case. So norm T is given by the matrix, diagonal matrix with diagonal entries lambda 1, lambda 2, so on lambda n with respect to the standard orthogonal basis of C power n. So as in the earlier case, we can easily check that norm of T is exactly maximum of mod lambda 1, mod lambda 2, mod lambda n. Okay. So given a diagonal matrix with the diagonal entries lambda 1, lambda 2, so on lambda n, you are able to get a linear map. So we can actually check whatever the maps that we have defined earlier. This is linear. T is so linearity is easy to check, and the second case also it is easy to check that T is linear. So check that and using a diagonal matrix we are able to get a linear transformation, and we also found the norm of T. So let us look at A to be n by n matrix Aij. This is MNC, that is let us take n by n, m by n. So set of all m by n matrices, m by n complex matrices. Okay, define T of x is Ax. Now A is a transformation, A can be viewed as a transformation from Cn to Cm. So A acts on Cn, so T is a map from Cn to Cm. Now show that T is bounded and find norm of the operator. Okay. So this is about finding the norm of an operator. We can also view this norm of an operator in a slightly different way. So define, so let us fix a notation. So let us write S suffix h as set of all x in h such that norm x equal to 1. So the unit circle. In H1. Now when T is bounded, let T be a bounded linear transformation from H1 into H2. Define a map phi from unit sphere of H1 into C by phi of x as norm of Tx. X is coming from the unit sphere. Then we can show that norm of T is exactly supreme of the function phi x, where x is coming from unit sphere. So if there exists a x in the unit sphere such that norm Tx equal to supreme of the phi x, so that is norm T. Such an operator we call as norm attaining operator. So definition, a bounded linear transformation or operator is said to be a norm attaining operator if there exists x in the unit sphere of H1 such that norm Tx is exactly norm T. That means the norm is attained at the supremum. In that case, we can say that supremum become maximum. So, whatever the examples we have discussed, finite dimensional operators on finite dimensional space, the supremum is replaced by maximum. We were able to find a unit vector where the norm of the operator is attained. So, the examples that we have given are examples of norm attaining operators. In the next class, we will be looking at, we will be finding out norm of operators where actually the operator need not be norm attaining, but we can actually find out the norm of the operator. So, we will be looking at those points. Thank you.